Welcome to this summary video where I'm going to attempt to summarize the Diploma Program Physics topic 2.4 Momentum and Impulse. So first of all, what is momentum? Well, it's a vector quantity. It's given the little symbol p, and it's simply the product of mass times velocity. So since velocity is a vector product and a vector and mass is simply a scalar, then multiplying a vector by a scalar gives you a vector, and that is momentum. So it's very important to note that momentum has a magnitude and a direction. The units, mass has units kilograms and velocity has units meters per second. The unit is the kilogram meter per second. Impulse is simply defined as the change in momentum, delta p. So it has the same units as momentum. However, there's a link between Newton's second law and momentum, because if you recall, Newton's second law says that F equals ma. Well, a is the acceleration, is the rate of change of velocity, delta v over delta t, but now we have this new quantity, momentum, which is mass times velocity. So F, the resultant force, is equal to the change in momentum divided by the change in time, because mass times a change in velocity is the change in momentum. So we can express Newton's second law in terms of the rate of change of momentum. So the resultant force, if there is a resultant force, it will be the same as the rate of change of momentum. Now, if you look at this, if we multiply up, if you like, we get that the force is equal to, or sorry, if we multiply up by delta t, we get that the change in momentum, which is equal to the impulse, which I have down here, is equal to the force times the change in time, delta t, which, if I just move this over here, force times the time, if I was to plot force on the y against time in the t, then if I have a varying force over time, which is quite often in a case of an impact, then because force times time is the impulse, the area under the force time graphs gives the impulse, or the change in momentum. Now another important principle that you need to learn, and that comes up in other topics, is what's called the conservation of linear momentum. And basically, in all situations, if we were to add up, if we have two situations where we have a before and an after, and we add up the momentum before and the momentum after, we actually find that momentum before equals the momentum after. This is the conservation of linear momentum. And when we have collisions, so if we were to have in the before and after, if I was to collide a mass m1 with another stationary mass m2, and I know the velocity before is u, and the situation after is that they stick together and they move away as one body afterwards, v, if I was to know the velocity before, say 2 meters per second, and I know their masses, and the only thing I didn't know is velocity, then using the conservation of momentum I could solve this problem. However, there are three different types of collisions that can occur. One is elastic collisions, one is inelastic, and the other one is explosions. Now, what do we mean by inelastic, elastic, inelastic, and explosions? An elastic collision is when we have two bodies colliding and then they move off as separate bodies. In elastic collisions, we have momentum is conserved because momentum is always conserved, but kinetic energy, which we talked about in a previous summary, is not, sorry. In elastic collisions, momentum is conserved and kinetic energy is conserved, which means if we were to add up all the kinetic energies before and after, it would equal the kinetic energies before and after would equal. However, in an inelastic collision, which is often the case when the two bodies would collide and then merge and then move away as one body afterwards, then momentum is conserved because momentum is conserved in all types of collisions. However, but not kinetic energy is conserved. In an explosion, it's the opposite to an inelastic collision. We start with the bodies being separate, and then they explode and move away in different directions. This is the same situation as an inelastic collision. Momentum is conserved, but kinetic energy is not conserved. We should also add that we can express kinetic energy in terms of momentum, because kinetic energy is equal to a half mv squared, which is the same as a half m squared v squared divided by m, which is the same as a half times p squared divided by m. So we have, because p, momentum, is the same as mass times velocity, so this quantity here on the top, m squared v squared, is the same as p. So we have an alternate expression for kinetic energy, which is momentum squared divided by twice the mass.